that you cannot see the screen flashing telling you it's recording is because I don't use the normal online method. Obviously signal can get good, can get bad. If Wi-Fi signal dies, you guys get a really bad signal and it will record that as well. So what I tend to do is I record to my hard drive, convert them, and then upload them afterwards, so that even if that signal starts to go a bit dodgy, I've still got a nice consistent signal that you can actually see. 2 seconds. I'm just going to call you up the notes so you can see which ones I'm going to be referring to. I think it's this one. Please let it be this one. Yes, these are the ones. Now, this was just a component that I'd made up as we were going along. And I'll give you the geometry onto here. I do need to tidy up these drawings a bit. And all it is it's a 3-point component. Now we are going to be visiting this today, but what I wanted to do first is just come back onto the using of geometry and the ability of being able to import directly from geometry. So I'm just going to show you where the material is. So on here, see on here we got Comsol dog bone. I'm just going to download that. And then minimize that. And I'm going to go to my Comsol. Again, I'm going to use 5.1, so I'm going to uClan remote access. In the file, you'll also find the parameter sets that I'd set up. So so in the file, on that download file, you will actually find, hang on a second, open a new window. On here, you will actually find the Comsol dog bone, and you'll find it in a folder. So I'm just going to stick that on my desktop, and I'll just get rid of that. And in here, you will find the parameter set, and this always loads. I don't know why this is tied to it now. You'll find the parameter set, and you'll also find the dog bone step file. Now, the reason I did this is this was the original geometry that I made in Comsol, and it was not playing ball with me, but there is some really important things that I do want to pull out of it. If any of you don't know, I am dyslexic, so I use read and write just to make sure that there's something, that I'm not writing something totally daft. So that's why that keeps appearing, but I don't know why it's just randomly appearing all the time. It's a little bit irritating. There we go. Right, so I'm into Comsol, and again, just to show you what I've done, I've downloaded the Comsol dog bone, and this is just a little bit of extra thing that I wanted to add in because I know that we didn't get to see it, and it is a really useful tool, So let me come back and then come into here, and then what I'm going to do is I'm going to speed this process up drastically. So I'm going to go Wizard, 3D, Structural, Study. I'm going to do a stationary. So the time dependency I'm going to move into next week, by the way. I really do want you to see the time dependency and the benefits of both. So I'm going to go stationary. Right. Now on here, the thing that's different is we've got a dog bone geometry. So I've given you that geometry. But what I'd like to do is I'd like to just get them parameters put in that I originally had. So I'm going to right click, go to parameters, and I'm going to open. Well, load. And what you'll see here is, just open that up a bit. This is my uClan drive here. However, down here I've actually got my drive. Now I nicknamed my PC Helga. So what I'm going to do on here is I'm just going to navigate to my user. and all I'm doing is just navigating to where it actually is stored. Now, if you don't see your access to your local drive on your PC, if you don't see that, what you'll have to do is use file share or my files, which is here. But I'm hoping that you do see it. So again, I'm just going to navigate myself all the way back up to the top, and what you're looking for is local disk. And I'm hoping that you do see that. So if I now navigate down to my local disk, and all I'm trying to do now is navigate right to my desktop on this PC, and I'm just going to use it from there. So again, I've navigated down, and then when you go to your local drive, I'm just going to navigate down to my user, which is me, and it's going to be your private name, and then on there you will find desktop, and for me it's there. So if I click on there and then open, what it will do is load everything in. Only thing that irritates me here is that for some reason that just went belly up on me. It's not really a value that we need, because obviously we were going to import the geometry, but it'd be nice for it to work right. Why it did that, I'm not 100% sure. And yeah, so now it's actually fixed. Now it's actually, and for some reason A just does not want to play ball. So all I've done there is just imported the geometry. Now, what's extra on here that we were doing as to last week? All these values here, all these are mapped against the ASTM standard. I've just brought them in directly from there. The most important thing here is this. I'm just going to move that down. This is a variable that I set up called, it's parameter. We could call it counter. We could call it multiplier. And what this is going to do is this is going to allow us to cycle. We can do all sorts with this type of thing, but we can intermittently introduce a cycle process, and we can slowly introduce force to something to see the overall response of what something's doing. Now again, we're not doing modeling, so really all these values here are all just really there from last week's example. But what I'm interested in doing is importing the geometry so we can actually do this variant force that I wanted to show you. It's a really useful tool. So what I'm going to do is go to geometry. 2 seconds. The trouble is let me see if I can make these parameters bigger. Now it's normally in font. 2 seconds. Let me just see if I can go on to my.
Just use second tool and paste it in the chat.
That's a good shout. 2 seconds. I'll just see if I can make. I'll see if just manually changing through here will make me a bigger. No, I think you're right. Right, 2 seconds. I will do that. So let me take a snip of that. There we go. Right, so I'll stick that in the chat, and then you can all see that. Again, these parameters have all come. That's coming straight from that import that I've just given you. So it's nothing. Hang on a minute. Here it comes. That's the one. So it's nothing that you don't have, if you will. 2 seconds. I think I've got another comment coming in. Whoops, wrong side. No, I don't. It's all right. Somebody else speaking to me about something else. So these are the parameters. And again, I don't want to spend too much time here, but I do really want to show you this tool. So again, it's parameter, it's para. You can call it counter, you can call it variant, you can call it anything you want really. Doesn't really matter. But this is our golden child in all this. So what I'm going to do is go to geometry. Now, this is something that you must be very enough. Now, I made this mistake during PhD. I'll try not go into too much of a tangent on this, but I made this mistake during PhD. I was looking at the KTM 525, and I was looking at the piston traveling up the cylinder. And as it's traveling up the cylinder, what I wanted to look at is the dynamics, so the torsional twist of the variant piston ring. And when I brought it in, the values were coming back 1,000 times bigger. I'm thinking, what have I done wrong? What? I don't understand. This was a week, me dicking around. And I realised this was set to meters. You go, no. So even imports, when you import, if you set this wrong, this can come in massive. So do keep this in mind, because I didn't realise. I genuinely didn't realise. And a great thing to also take into consideration here, look at that. For those of you who are massive nerds into any types of nanocomposite materials or behaviours of materials, 3D prints, composite 3D printed materials, you've got nanometers you can operate to. You can look at species of interruptions in chemicals. It's crazy what you can do. If you're looking at hyperelastic performances of a neoprene rubber or anything like that, or molybdenum, you want to look at molybdenum and the dry lubrication regime of that system. You can do all that. It's crazy. Anyway, I'm going millimeters. So I did try to stay away too much from that tangent, but it's crazy what you can do. Anyway, so onto my geometry. I'm going to extend on my geometry. I'm going to right click and I'm going to go import. Now on my import tool, this sadly, when it comes to this type of tool on bigger things, you do actually have to purchase this as a tool, the import tool. So, but what I'm going to do is I'm going to browse, and I'm going to navigate myself again, scroll down. Again, I'm just navigating across. This may take a little bit of time because what it's doing is it's passing that data backwards and forwards. I don't imagine it take that much time, but you never know. So you see there, I've navigated across and dog-bone step. I'm going to left click and then open. What it does here is it says objects to import. Do you want them solids? Do you want them surfaces? How would you like the surfaces to be resolved? I'd like them all to be, I'll leave them in this format. And what we'll do is examine it and make sure that it's something we can operate to. So what I'll do is click build all. 3, 2, 1. And just imagine this session last week would have been so much quicker if we'd have done it this way. So much quicker. But that's it. We're now operating. So if I drop surfaces and then do import again, I want you to see the differences of what's happening, that's all. So I drop surfaces completely. And then what actually happens is, because I've dropped surfaces, it refuses to try and bring any surfaces in and ensures what I'm getting is a solid. It's not something you've got to ignore. You can come back and you can check it again. You can do different things, make sure it's right. And when you go to your import, you've got import absolute tolerances. Anybody who's CAD savvy, which I know there are a few of you, you will know that when you output geometry from a CAD system, what it ends up with a relevant tolerance of where surfaces interface with each other. If these surfaces, I call them illegal, but if these surfaces protrude past each other, if there's any illegal penetrations between multiple geometry sets, it will just do it. And what you'll end up with is like a, or as my lecturer used to call it, geometry fart, where you import it and it's just not right. What this system tries to do is to try and merge these elements together. Those of you who are surfaces, so you know about surface modeling, you'll know that when you bring things in, you've got to try and knit things together. Now, by me switching off the surfaces, all I've done there is said, look, give me solid. If you don't give me solid, then I'm not interested. And that's all I've done. What you really got to do is play around, get used to it, and get. I mean, this is just a single geometry, but we are going to do an assembly today. So this is just a single one. From here, when it comes in all geometry sets, it asks you what type of geometry is it. Is it freely flowing between it? Is there lots of random bits all over the place? Does it need to be brought in with its own entity area? Or can the single entity be assumed to be working together like a union? So this is really, and this has been the biggest criticism of MATLAB and Comsol for years. It says form a union. Now, for us engineers, we'll know forming a union means that you're actually making a solid-based assembly where it won't allow for movement around it. The system can actually operate and know what multiple geometries are trying to do, and that's what this will do. And it's really deceiving because if I click down, it says form an assembly, and you kind of go, what? Now with this, we're just saying form a union, single part. But when we move to the assembly, we're still going to form a union, and you kind of go, really doesn't make sense. But trust me, it does. Well, it will do. So we've brought the geometry in. Now, again, I don't want to spend an awful lot of time doing this. You'll know that last week we chose a structural steel. Just for completion of the notes, and just to show you an easier way for completing on this, I am going to go back to my materials again. I'm going to right click, and then I'm going to go add material. And I've already got this selected. It's because I've used it so much. You guys will probably find the same. So I'm going to stick structural steel. You can choose something else if you want to be a little brave with it. So I can choose structural steel into there, and now it's gone in. As ever, 200 to the 9, and with 200 to the 9. So this is all still comparable. The issue is though that we don't really have that all important geometry control that we wanted, which is a bit disappointing. Right, so what I'm going to do from here is I'm going to bring this across. Right, 2 seconds. I'm just going to close my office door. So let me just pause for a second. I just need to close my office door. Right, so again, getting back to it, moving relatively swift now. Right click, and I'm going to go to fixed geometry, fixed constraint. Apologies. Under my fixed constraint, trying to replicate where this thing would be fixed. I'm going to click on here, and click here and here. So we've now got that back end constraint there, and that will be in essence where it would be fixed. And then what I want to do now is pull it apart like you'd get in any good reputable Tinius Olsen or anything like that. So from there, I'm going to do what's called a boundary loading. Now, boundaries refer to its areas, faces, if you will, for all you CAD savvy people. Faces. The boundary loading refers to areas for which I'm going to hold fixed to. So again, if I come back here, that is my fixed area. Now I want to do my boundary loaded area. So here, 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 and here. So again, we're now fixed and we're loaded in that key particular area. Now this is what, I'm just going to get to it. This is why I've been trying to get this working. And this is the big important bit for me, what I really wanted to learn from it. So if I go to total force, under my total force now, as you know, last week we were selecting, where is my P? Oh, LF, sorry. So longitudinal loading was 20,000. So what I'll now do is go back to my geometry. And given that I'm moving in X, what I'm going to do is call this LF. Right? Now, the thing that's confusing now is what I would like to do is attach a range to this. So every 0.1 of a second, I'd like to measure how it's moving, but I'd like to make that measurable, if you will. So it as a 0.1 of a second, I'd like to look at force being applied, but I'm going to do that as a subdivide, just because. Now the reason I can do it as a subdivide is I know that the overall top of this will be 20,000 kilonewtons. Well, what I'll do is I'll do it over 1 second, but I'll do 0.1 iterations, and I'll divide that out. So what it will do is we'll divide that 20,000 and multiply it by that 0.1 of a second. So I know it's confusing. So if you look here, I'm actually going to start at 0 and I'm going to move to 1. Now the best way for us to be able to do this at this point is to multiply it by para. Now this again is just the variable. To just pan back to what I'm talking about here, that is there. Now under my para, it starts off at 0, but it still doesn't I've not really told it, still not told it how I'm going to have these iterative changes, these builds over the top. Now some may know this as a parametric sweep. It's kind of a parametric sweep. It's almost the go-between. Parametric sweep is the one that we've not actually done as of yet, but I do intend to even squeeze in a parametric sweep in there, just because we need the geometry to be dead straightforward, because if we don't, it can take 6 to 7 hours for a solution to be done. But anyway, before I go on a massive tangent, what I've done now is I'm going to go to my mesh, and I'm just going to mesh it as normal for a start. So I'm going to build that mesh. Now before I do anything, in everybody's experience so far, is that any good? I'll start. No. You got to think this thing is moving longitudinal, so it's moving along that X component. If it's moving along that X component, that is no way any good. It's tetrahedron, and it's made an entirely wrong assumption for me. So what I'll do is I'm just going to knock it down to something a little finer, because even the size of it, now that type of size is not a bad start as far as the sizing goes. So what I'm referring to here is the actual distance between each nodes. It's not a bad start to give me a good assumption of what this will do under its extension. But I still know that that's not quite right, because if you look, I mean, I know if I run this through the analysis now, I know it's going to come back with a result that's going to look a bit shoddy and a bit shit, in lack of better words, and I want to get that right. So if you look to the right, I've got sequence controlled by physics controlled mesh. What I'd like to do is I'd like to control this a little further. So I'm going to drop that and go to user controlled mesh. Now, not to here, like that. Now what we've got here is a little bit more that we can do. So first things first, I'm going to right click and I want to take a look through my meshing options. Now let's have a look. Now I know, well, I mean, you should be starting to really realize that something like a tetrahedron in this case is not really going to do its job. Tetrahedrons in some cases around here, but I think we need to combine quadrilaterals with tetrahedrons to give a better representation of what it is that we're attempting to do. So I'm going to right click and then go to more options, and we've got free quad. So under free quad here, I'm just going to bring this up to this one here. Under my free quad base, a few things I could do. What I can do is I can say, right, use free quads on the entire geometry, then use tetrahedrons on the entire geometry, and then it'll try and combine the two to give the best representation. That's what I'm going to try. So I could just click on entire geometry, just say, look, do the whole thing. So I'll build that as a start, so build selected.
Out of interest, with the boundary loads being on the extremities of the dog bones, not really necessary to analyse those, is it?
No, I know. Yeah, you're right. Now, the only reason I'd put it on there is it does simplify that process, but I think that's a good point, Mike. Let me just come back then. Let's go boundaries. See, if I go boundaries, if anybody didn't catch what Mike was saying, it was his point is that these are the boundary constraint areas. So really, why would we put a lot of emphasis on that? And he's got a good point. Why would we? Our biggest area of concern here is where the fillet is through to the gauge area. So I'll start by just applying it to here then, because I agree. I'll apply it to here. Really, as we know with dog bones, we do really know that it kind of appears in these areas or around the fillet. So just for argument's sake, I'm just gonna use them there as well. I think that's a little bit excessive, but we'll certainly find out. So what I'll do is just build that, and what we'll find by building this as a selected, it will now isolate everything else and give me just that area. So now you see here I've got scaled, I've got controlled areas, divisions of interaction. I can actually make that higher, so I could go 8 if you wish. So I'll show you what it does. If I do build selected, it just offers a little bit refined in particular areas. Now for what we're doing, I'm going to stay with 4 because I'm going to use a different tool here. So this just gives us this particular point, and then if I go free tetrahedron, right, okay, yes. So now what it's complaining about is, if I come back in, if you come into here, boundary mesh must consist of triangular system only, right? So what it's actually referring to here is it's saying it's struggling to get this transition between the two. There's a few things we can try. So if I come back onto my domains, it's just to do with the constriction that it's got. I bet it's going to be a massive douchebag with that. 2 seconds. Right, sorry, I just had a question come through or something else that can wait. So what I'd like to do first is I'm going to see if I can fix the geometries this way, and let me come to here, minimize, change that, and then build on there. Do you see where you got these domains it's talking about? That's what it's frustrated with. It's frustrated with them interactions there. But what I'll do is see if I don't like just changing the overall because it seems a little bit clumsy. Yeah, it does seem a little bit clumsy just changing the overall. Okay. So I may have to go right click and I'm going to introduce a size. Now the reason I've done that is if I just do that, if I just put it there, what I'm doing is dragging it up. Swine, it's not giving me one. Oh, 1 second. Let me just remove that completely. Delete. Yep. And I'm going to put my free tetrahedron back in. I've made a farce of that all over the place. So I'll put that onto there, and then I'm going to go right click and size. And this size really wants to be beneath. So in fact, let's go right click and bring in a size. The reason I'm doing this is I want to be able to control the tetrahedron. So that's what will do it. So you see how we've got size here to control the free quads. Then we'll have a second size which will refer to boundary area. I'm going to see if I can control these sizes. If not, what we'll have to do is we'll go back to the idea of just meshing over the two. And I'll make this, let's see if extra fine does it. Extra fine. So I'm going to build, let's see if it complains. It might still complain. Yeah, it's not happy with that. So what I'll do is I'm going to delete my free tetrahedron, and I'm going to delete the sizing on here, and I'm going to stay with my quads. I know quadrilateral will be far superior in this anyway, and what I'll do is say entire geometry and then build. It allows me to solve this relatively quickly, and what I'll do with that is I'll just knock it to a nice fine size, leave it like that. There is a particular way we could actually build it around here and sweep it along. There's all different ways, but I don't want to go on a huge tangent on this just because there is a bigger thing that I wanted to emphasize. So again, because it's under that extension, what I'll now do is go to my study. Now, what I was talking about with here, I want that intermittent change. I want to set up a nice range. Now this range, I want it to start at 0. I want it to increment itself. Let me think. If we go 0.1, it will be at this forever, and we'll end up with lots of iterations. So I'll probably go a little bit quicker, so I'll go 0.025. If you wish, you can set it to 0.1, and what we'll do is get the result, and then we can see that variant change. So what I'll do is go to study. Now this we've not really seen. Sorry. This we've not really seen. Now under our study, what we're looking for is study extensions. And you look onto here and you kind of go, ooh, not sure what this is. I know when I first did this, I kind of looked and thought, I don't know if I'm doing this right. Trust me, we are. If I go to auxiliary sweep, and then I am going to go add. And all that did is this now reads directly from the parameter list that we set up right at the beginning. I'm going to drop this and I can choose what I want. And I'm going to use para. So this initially gives me my starting key point. Now, anybody who's used to doing Excel, you'll know the term range. Anybody who's used to C programming, you'll know range. Anybody who's used to Arduino controllers, you'll know range. And range is range. So I'm going to go range. And I'm going to open a bracket. Now, for those of you who don't do coding, bracket, they call it argument. So I'm going to open an argument. I'm going to start at a 0 point range and go 0.025 for iteration. And then what I'm going to do is say, right, I'm going to start there, but what I want to do is move in multiples of that. Now, if I want to move in multiples of that, all I'm going to do is say 0.025. So then it says, at the next iteration point state, I'm going to move 0.025 and just add them up. As it goes through, what it does is it applies that to the force, multiplies that into the force, and then we get a gradual build on the force. Then if I go comma and 1. So what that comma is doing now is it just says, right, I'm going to go from this level to the force right to the full maximum force. And then there is our range set. If you are curious, everybody's curious when it comes to this, and you want to see something going on, because when you start adding ranges, if something goes wrong, you don't really know if it's worked. So what I'm going to do is save that. I need to save that because we're getting to a nice point that this may not work if I don't do this right. So what I'll do is just call this Comsol Dogbone. And save. Takes a minute because now I'm actually saving across the network, because this is now saving to my desktop. Give it 2 minutes, and there we go. So I'm now saved, I'm now ready, I've got the mesh ready to go. The only thing I haven't done is results while solving. This is sweet, I really like this. So if I go plot, and you can see where you got default plots, or I can go, I may need to add a stress plot in there actually. So default, what it will do is it should plot the stress and deformation over these iterative changes. Right, and if you have done it, if you've all set up, you should now be able to compute. And now we wait. Great. Let's have a look. Stationary solvers not converged. That's very strange. Let's have a look. Come to here. That's caught me off guard because that should not encounter resulting solver. Unexpected size. Or size of render data. Oh, damn it! This is to do with more problems. This is to do with the size in which I'm trying to do. So I'm going to try and remove that plot out and see if that'll allow it. Basically, when it runs, it will continually try to render. Let's have a check. So I've got my materials in, got my boundaries. Coincidence. Two seconds. Ah, right. So it's complaining about meshing now. At domain 1. What I'll do is, just to be sure, I'm going to add that tetrahedron back in, and I'm going to click on remaining. Domain 1 is not being meshed. That went a little bit pear-shaped. Bring this back up to fine. Not happy with me doing what I did, and let's go domain. Still probably going to complain with that. Right, 2 seconds. I just want to see if it's going to still have my issues with. Oh, hang on a second. I'll tell you what this might be. Let's have a look at my longitudinal loading. No, LF into parameter. guys. Give me 2 seconds. Okay, what I am going to do is just see if there is something missing.
If the force that's loaded, it looks like it's compressive rather than tensile.
Yeah, but it should have. Now, what it's complaining about is complaining that part of the meshing on here hasn't been completed. So I'm just going to reset it by using the system-based one, like that. And then I'll come back onto here and I'm just going to try and drop in that 3 quads. And then bring up my 3 quads a little bit to here. And then I will do my entire geometry and see if, yeah, it's still complaining of that same set, convergence triangles as surface. Okay, so let me just bring it down a little bit. Yeah, they're counteracting each other, which is pain in the arse. Totally get that. So what I'm going to do is just minimize that for the minute, and just see if my quads are causing problems on that. So let's run it again. I'm just curious now to see if it's the quads that are causing problems on that, which is another problem for me to solve. Yay! Right, so it's taking a lot longer now, and it's because the convergence between something on quads and something in tetrahedron is massive. So you'll see now it's taking an awful lot longer. This is coming from the quads. Now, I think the big problem here is actually coming from the flat faces. And I think from some of these edging as well. So yeah, I do need to get an adaptive element onto there, so that they can adapt between the two. So if I look at now, let's see how progress is going. So you see here, this tells us at what iteration it's at and how far it's moved. Yeah, it's moving miles.
Either I did something wrong or I have NASA's supercomputer, because mine just plotted it.
No, well, no, it's because I've been. Oh, hang on a minute though, Adam. Have you introduced your parameter sets? Have you introduced the range?
Yeah, 0.025.
Oh,
1.
shut up! You're just showing off now.
I try.
Yes, well, all we're getting now is it's building up, and you can see now mine's speeding up. Mine was a little bit rusty, clearly, and all it's doing is it's iterating across the whole process of it. If you are doing something like a 3D printed material, it is often quite useful to understand how that force has been translated across. You can do all sorts with this. You can really plot an awful lot out of this. These quads have annoyed me a little bit. I've been spoiled with the 5.6. I really have. There's so many little bits of tuning that's just added on there that you're like able to do. I forgot that you got to build the way that you got to build on here, but it is still going to give us a pleasant solution. So I'm just going to let that run through. And nearly there, and that's what we get. So I've got my stress result. Now, what you can see there though is, if I was to look at the von Misers on there, we end up with, I mean, let's just drop in a max and minimum. because you can never really tell. You look and you go, right, I've just got that, what's it really telling me? But if I go on to my results and I go on to more, where is it? I've got max and minimums. So in fact, I wonder if I can get it from here. More plots, there we go. So I'll go max and minimum for volume sets and then click on plot. Oh, now if I want to see just a value to telling me what that is, you see here it's set to displacement. What I'd like it to be is set to von Mises. So I'll click onto my plot here and I'm simply going to copy that expression. Come across to my von Mises and I'm going to paste that in, and what it will do is give me a plot of the maximum. So you see there, it's actually at 4 to the power of 6. Now you look at the plots that we'd actually calculated out for our sigma. It was 1 to the power, 1.5 to the power of 8. Now this can instantly make you think, what have I done wrong? You've actually done nothing wrong. Look at that. The parameter values that we're looking at the moment is step 1. If I wanted to look at what happens to the actual to the dog bone at 0.2 and then click plot, what you start to see is at that point the stress really rises at at that particular point right there. But if I jump it right up to what happens right at the end, we've got 1.6 to the power of 8. It's still going to be out as this. I know it's going to be out, but 1.5 to the power of 8. And it's really because of that plot. Now, I'm with Mike, I think. I mean, if you look at that, looks like it's gone into compression. If you look here, that's where it's held. Then you look here, it's moved upwards, hasn't it? So if you remember, Mike was noting earlier, is this moving inwards? You're right, Mike, it was. And that's probably why my plot took a little bit longer. So on here, I'm just going to knock that back to there. And that just allows it to move that negative. So yeah, I should have noticed that from the start, but you're right. Right, so that's really what I wanted to show you on the dog bone. When it comes to this quad, that's a swine, is that? I'm not sure why that didn't actually play ball like I wanted it to. What I probably need to do is define this a little bit better. I'll take a look at that and get that even tidied up even more. But it is just a factor of just playing around with the mesh, trying to get it into a quad-based scenario, because I know quads give a far better result. So if I like plot like that, and then if I do full plot, it'll go no. But if I wonder if I can actually, I'm just really curious now, so apologies. If I can actually just pluck out these key important areas and see if it'll let me plot like that. So let's try that. Intelligent which problem occurred. Let me see if I can make these divisions.
Well, I'm thinking, I don't think you need to put a mesh on the boundaries because you're not going to analyse it. Or does it still need to have some form of mesh on it?
No, it still needs to know, because if we just look back on here, you'll see there that there is levels of deformation.
Right.
So it's, even though, you're absolutely right, even though it's not really being taken into consideration, you do kind of sit there and go, well, it does need to be there. But you're starting to really realise on the bigger aspect of how much do you actually need these to be there from the start, because this is the target area, isn't it? The gauge area itself. So a lot of people do start to look and go, well, can we minimise and remove them and just have an equivalent to allow that to move? Anyway, that is the dog bone. Now, again, I do really want to move on to this assembly, because the assemblies is where it's all at, really. So I'm going to save that. In fact, let me just, I'm going to just disable that for the minute, and I will revisit that to get that working, to get that a bit more efficient. And I'm just going to run that through again. what it is I'm going to upload this model. I want you all to have this particular model. I'm just running it through again. I honestly don't know, Adam, why yours solved so. Oh no, saying that mine's solving quick now. See, it's because I was compressing, not because I pushed it in the wrong direction. That's my excuse.
The future's now, Matt.
Clearly. Any minute now. Again, I'm just running this through because if anybody wants to open this and look at this import version, then I want everybody to be able to see it. I am keen to get this assignment out really quick as well, because obviously in an ideal world we'd have all the time in the world, and I want to try and run this deadline right to a good level, a good position. Now, it's just because I want to give you a lot of time, because don't forget, we'll just get to a point where you just can't have any more extensions, just because it'll all just be signed out. I'm just interested now. I wonder what my maximum comes out as. Yeah, it's not really going to change, but it is still at 1.6. Which we calculate out to 1.5. You can get it to 1.54 if I can get this blooming quads working right. But you can get it to 1.54. But my point is that we end up with a good comparative value to what we've been operating to, and this is stress is due to that. Now the rest of them you can also pull out, so the maximum extension, the delta, so the length due to deformation and strain. You can pull all these out, and these will give you a nice comparative value.
Question about Comsol. Could you simulate over a span of time what would happen to the material if you continuously compressed and extended it?
You mean put it through model analysis? So it's I tell you where this gets used a lot, in blades. So if blades are, I'm waving my hand, but if blades are oscillating, if you've got wings that are oscillating over a particular time, you can do that as well. You can do fatigue, and the trouble is I don't often have a lot of fatigue in these notes, but I think I'll gladly add a bit of fatigue stuff in there if anybody's interested to see that. To be fair, there is just so much that all I can really do is try and set up the basic foundations. But if anybody is interested, please do drop me a line, and I'll just set up an extra. This is fatigue, and I'll set up an extra things as well. Again, I just don't want to push too many people on a tangent and then leave you really confused with so many different things. But yes, in short, Adam, there is a lot you can do with it, and you can simulate things like that. Right, what I'm going to do, hit save, and I'm going to start a new model. I'm going to do exactly what I'd originally said from the start. Now, this is the chuck, or the yoke, or whatever you want to call it. It's that as an assembly. Now, what we're going to do is we're going to hold this from the base area here, and then we're going to apply 1,000 pascals, not much, onto this face, and we're attempting to actually pull this apart. This is an assembly of 3 components: yoke, block, pin. Then what we're going to do is we're going to look to see if it's given us something that we'd expect to see. Now, for anybody who's already in industry, you'll know this inside out. You grab these, and if you pull it apart, I say anybody in industry, anybody who's common sense really, if you pull this apart, you can assume a few things. The way that the yoke is designed, it is a U bracket. So you know if you try to pull that apart, the first thing that it's going to try and do is emulate that Y shape. It's going to bend outwards. You'd instantly expect that. Now, given that there's radii to the back of the arms as well, you're going to expect that there's going to be high force there, high concentrated stress there as well. Now the other thing when you actually look at that is the first interface where the pin sits. When we actually go to grab it and pull it apart, imagining that pin area, the interface where the round face hits the round face of the yoke, surely that's going to be a high point of concentration also. It'll have to be, because that's going to be the direct spot where it's going to be interfacing. And what we want to see is if we can isolate these areas, make sure it's as refined as humanly possible, that it starts to look a little bit more sensible, and it's something that we can operate with. Now, again, what we're going to do here is we're going to use a predefined geometry. What I really wanted to do is I wanted to move away from any need to do modeling and any need to do any CAD. And I know that the modeling process is a little bit problematic, a little bit painful in many ways. So what I wanted to do is just introduce a couple of different ways. So where we have the geometry and importing that geometry and working with that geometry. So if you just navigate yourselves, in fact, I'll come back to this. If you just navigate yourselves over to Teams, 2 seconds, onto Teams. So let's get over to Teams and onto Teams here. If we come down and we go to Clever's Assembly mod, what I'm going to do is just download that. If anybody's worried, don't worry. I'm going to zip all these files together anyway, upload them, and then you guys can take a look at what I've been doing. Again, today I really just wanted to focus on the assemblies and really just wanted to focus on that iteration. So because we know, because we can be cocky now, because what we now know is we can run an iterative process on this. And that's what we're going to do. We're going to repeat that exact same process again. Let's get it to iterate and let's look at the cycling of what's happening. And then let's take a real in-depth look at what we can do with this. So what I'm going to do is go to my downloads. Because all I've done is just downloaded the Clever's assembly. So open a new window. There's the Clever's assembly mod. I'm going to drag that into my folder. I'm just putting all these in there because it just makes life easier. And you'll also find here as well, this is another different file type I've used. I've used IGIS, which is the old school method. So I'm onto here. Now, I'm happy with this now. I'm just going to save that. I'm going to start a new. So let's go new. I'm going to go Model Wizard. 3D part. Solids, and just to show you on here, we're gonna visit shell very soon, and shelling is going to be the last bit that I really want to take you through as far as geometry goes. And shelling is carbon fibers, things like that. So I'm going to go solid mechanics, add a solid mechanics. Going to go to study, going to go stationary, going to go done. Again, all this, so what I'll do is go back to my drawing. Oh, damn it. Forgot to put my units on here. Wow, I have so got a third class with that. It's in millimeters. Take it from me, it's in millimeters, even though it's not clear. So I'm going to go millimeters. Then I'm going to go to geometry, right click. I'm going to go import. Now you do have live links, but so you have a live link to SolidWorks. If anybody is interested and they're into SolidWorks, you do have a live link to SolidWorks where it will link directly, and when you make modification, it will automatically update SolidWorks to here. It's great. Anyhow, I'm going to go import because I've given you this geometry. So it wants to know a label. Let's just call this Clevis. Clevis. So I'm going to go in any importable file type. I'm going to go browse. And I'm still in that folder. I'm still on. I'm still across the network, still allowing me to do that. This is one thing that this system does really well. It always holds its position until you tell it differently. So I'm going to go Clever's Assembly, and then open. And on here again, we've got solids to surfaces. I'm going to drop the surfaces. I've got my relevant tolerance. There should not be any problem. I say that. There should not be any problems on this import, but let's import it and take a look. So let's build all objects. This makes it look like it's a huge in-depth assembly, but again, it's because it's operating across the network and it's just sending the data across, so it is a bit slower for that reason. I say that though, I bet you some of you have already got this built. Any minute now. And that's the Clevis, or the Clevis assembly. This is a classic assembly. This is something that has come across before, and it is something that is quite famous in a few examples that I've seen done before. What I'll do is let's run a simulation on this. Let's then just review these meshed areas. Then when we start to get some meshed areas, let's do a couple of modifications. Now I say modifications, I'm just going to chop some material away and see what type of result it has by doing that. Chopping the material is dead straightforward, and I'm going to take you through that. When it comes to here, it now says, are you building an assembly or a union? Now these are all connected, and what I'm actually going to do is say, look, they're all connected as a as a union, but not an assembly. And it's because I want them all to be in their own, I want them to be in a connected space, but I still want the domains to be there. I'll show you what I mean. So if I click build, it comes in, and you kind of go, oh, hang on, that's the, well, hang on a minute. But you look up here, I've got ways, so I can select all objects, or select domain areas. You see here, I can still select my key domains. So it's doing what I wanted it to do. It's still doing what I expected it to do. Right. I'm going to go parameters. Set myself a nice power, because I'm going to do the power again. Set that as 0. This is just a counter, don't forget. Counter. And we're going to go P. Let me just look at what, I can't remember what values I'd actually assigned to this. Cannot remember. There. Wow. I think we might change that. Seems a bit low, doesn't it? But let's just get this. So we've got that, and then we'll go PA, just to make sure that our units are correct. So square bracket, open, close square bracket, and then we'll call this applied pressure. So we've got our applied pressure, and now we're in a good position. We can first run it and take a look at what we're actually getting to see if it's something that we trust. I'm going to go to materials, and I'm going to go add material. Just for me, I'm just going to add in my structural steel, add it to the component sets. Now it comes in as all three. What I will do is, let's make, just for argument's sake, let's make the block of an aluminium. So I'll just choose 3003 aluminium, and I'm going to add that component. So I've now got two different materials. Whoops, oh, that went horribly wrong. Where have you gone? There you go. expand that. There we go. So I've now got two materials in here. Now when I first introduced that, this automatically assigned it to everything. I'm going to left click on there, and that now removes steel from being that. So the yoke is steel, the pin is steel, however our block is going to be aluminium. So now we have that variant in between the materials. Oh, sorry. Right, and based on the notes that we got fixed, and we're pulling from the actual base of the block. So again, I'm going to right click and I'm going to go fix constraint, spin this, click onto here, and then bring this back round. So it's told me it's fixed there. Got a green marker to tell me it's right. I'm going to right click. I'm going to go to boundary loading. I'm choosing my lower face here. Now, often if you're unsure what type of output you need to be, I mean, on here you've got your load parameters, your load defined by force per unit area. Or, again, we've got total force, which is what we were using for the dog bone. Or we've got pressure. So what this is now is obviously P. But what I'm going to do is I'm going to say P multiplied by para. Oh, excuse me. So we've now got that multiplied by para, and the only reason I'm doing it is I want that iterative change. I want to be able to see exactly what the process is actually doing, just for me to take a good look at it. That's the only reason that I'm doing it. First things first though, let's get a mesh built. I've just used default on this. It brings in warnings. Now these warnings just say you do have short areas that it's a little bit concerned with. And you know when you click on something you go, well, that is telling me bugger all. If I zoom and come across to here, you'll see here I've got transparent mode. And now if I click on the faces, where is it? They actually tend to appear down here. It's actually not glowing, but the 95 and 97 around here are the actual pin interface. Normally they should glow. That's really surprised me. It's always been one thing after another with this. Normally they should glow, but 95 and 97 do refer to them key particular areas. What I'd like to do though is I'm just going to presume that that will be the normal for the minute. So let's just make it a little bit finer. We'll go extra fine, one more step finer. And it still refers to the same because it's that area. But what you can start to see now, where we've got assemblies, you can start to see auto-adaptive coming into place. So you look across here, you can see that adaptivity being changed as it's going through, which is interesting. It's really good. We've got our force in, we've got our pressure in, we've got our fixed constraint in, and again I'm going to hit save on this because if it's going to fail, it's going to fail now. I'm going to go Clevis assembly. I'll just call it Clevis assembly, and then I'll go save. Last thing that we need to do is to set up our parameter set. Come onto my parameter set. I'm going to go onto my station rate, onto my study extension, onto my anxiety sweep, auxiliary sweep, anxiety sweep. And on here, if you remember, I'm going to try this again. It's going to go range. I'm going to use the same parameters, 0.025, and then offer it in multiples of 0.025, and then I want it to run to the value of 1. So that's just the multiples of the pressure output. And that is done. Again, just going to hit save. Oh, come on. And now I'm going to go compute. Now this will take a few minutes. It took a few minutes to solve a simple dog bone, so this will definitely take a few minutes. And all I'm doing now is going to run it through, and then we're just going to see if it's given us something like we'd expect. As ever, you kind of sit there and you do need to use your savviness, if you will. You do need to keep in mind about what something's doing, just to give you an idea if something is correct or not. Now, the one thing that we've not really visited as of yet, we're going to do in a moment, is we've not looked at being able to navigate around different components, being able to just check refinements and meshing on different components. What I really do want to do is I want to look at that pin, because it is the pin. This is what I'm alluding to. It's the pin that causes the big problems. When we actually ran the meshing then, it did return with a warning around that pin. We're probably not going to be able to eradicate all the warnings completely, because it just says, what it's trying to say is these areas could do with further refinement. And the trouble is if we keep going and going and going, because we're using the online version, it will take further and further time to get that most accurate solve. So we're going to rule out that we're not going to worry too much about a couple of these warnings that will come up when it solves. While we're sat here waiting, is there any questions about what we've been doing? Let me just pan over to here. Let me just see for any possible questions. Nope. Okay, brilliant. I'm still at 1%. I tell you, maybe I shouldn't have done. If I didn't do a parametric sweep, what it would actually do. If I didn't do the sweep on it, what it would actually do is just run it. But I was interested to see the whole process with it. To speed this up, what I may do is drop the sweep, just because I do want to get. I want to physically get to a result before before this session ends, and I want to really emphasize on that mesh. If you look there, my parametric, I'm still at 0.025 of a second. If it doesn't resolve itself in a moment, I'm probably going to cancel it and just turn off the sweep. It's just taking too long, and I don't want to lose any more time with this. Good question. Right. So I've had a question through about heat transfer and fluid flow on Comsol. it's outside of the structural mechanics that we do, but I can definitely do something to support that. Yeah, I can definitely put something in there to support that. It's a good one, and yeah, I can definitely add something in there for you to take a look at with it. So now the statement is that you're asking about heat transfer and fluid flow. Are you referring to this as being multi-physics? So you want the heat transfer to be affecting on that fluid flow and vice versa, or you want the fluid to generate? You want the fluid to flow with it, but you want heat to be generated, so you can actually look at the effect on the material.
Well, I can answer this one.
Oh, that would be even better. Yeah, go on.
Because I'm trying to run a simulation on a solar panel heating up, and so the wind that's passing over it to kind of increase the heat transfer. So
Okay.
it is, I believe, that is multi-physics.
That is multi-physics. Yes, that's right. Now, 2 seconds. It is something definitely that Comsol have loved to talk about for a long time, is solar panels and their ability of how they perform. So yeah, I can. But what my point is with that, Adam, is there is lots of stuff out there at the minute that will give you good guidance into literally what it is that you're looking at, because there is loads of people that have been looking at it, loads of it. It's some great stuff for you to build on. Right, it's running too long, is that? So I'm just going to cancel this. It's just because it's taking such a long time to actually solve it through, and it's because I'm running it. I'm not running it from the uClan server. I'm running it across the entire thing. So what I'll do with this is I'm just going to switch off my sweep. I'm going to come back to my boundary, and I'm just going to drop my para out of it. And I want to get to that solution, because or else otherwise we're going to be sat here just twiddling the thumbs talking about the weekend. And I want to get something out of this because it's a bit irritating. Here we go. You see, this is what I'm used to. Look, it's nearly done. Thank God. And again, this is purely because it's running iterative small pieces. I do want to show you some bigger examples of this from my particular research that I've been doing, so on skeletons, just to show you that iteration process and why it's important. So for us, when we've been doing it, we've been doing nitrile, looking at nitrile hyperelasticity, but not just nitrile by itself. We've actually been looking at nitrile when it's inserted into components and its ability to flex. So we have hardened geometry that goes up the back of a human, and each piece of geometry acts like a spinal section. Each spinal segment then has hyperelastic materials that connect them all together, almost, if you will, a spinal column. And what we've had to do is to be able to model the two together as humans is restricting it with an actuation at it. So we're actually looking at the resistive force of the human body and the force that's being applied from the actuators, and then the resultant on the geometry and the hyperelasticity. It's a monstrous sim, huge sim, but the types of results we're getting are phenomenal. I can actually show you one. I can actually show you one of the prototype skeletons because I've literally got it here. So this is now pausing up as well, because I if you remember, I made the mesh a little bit finer. I need to just go with the original because I'm going to change it anyway. Right, hang on, I know what I'm going to do. Right. So I do want to actually start getting some key results with this. Now we've got everything pre-set up. I'm just going to use my version that I presently run on and that I operate with. I've got my 1000 pascals applied to it. The mesh that I'm running is looking like this. And then what I was attempting to do with it, and the reason I'm doing this is because I want to get some initial solution with this. So I'm going to go compute, and what this will do is this then runs through the overall cycle, and what you can see there is, again, I've still got that adaptive like behavior, but it's really clumsy around these areas. And is that actually solved? No, still not solved, is that? Bloody awful, is it? Right, so now I've got my convergence in there, so I'm onto my convergence. Now, oh, there we go. Now, let's have a look what we got. So onto his mesh, it's relatively fine. It is heavily concentrated on these areas. So if you look here, it does concentrate itself quite nicely onto these areas. And it's quite large, if I'm honest, onto them key point areas. My question would be, though, with it, is it a true reflection of what we should be getting? Now, you can see there that it's deflecting on the inside. Don't ever be fooled with some of these. It's basically it's implying that it's what's called got an exaggerator on it. So these scales that are on here, these scales are set to be, look at that. That is 145,200 times more than what it would actually deflect. Now what I need to know is how much has it deflected. So I'm just going to add another surface in there, and what I'll do is I'm just going to look at my displacement. Now if I plot on there you get 2, you kind of go, that's not what I was after. So I'm just going to hide that, so disable that for the minute, and that is what actually happens. Does pull it apart, and if you actually look there, we've got 6 to the minus 6 of displacement. It barely moves when it actually operates. Barely moves. What I would like to do, though, is I would like to be able to look at, has that even solved yet? I would actually like to look at the refinement of this meshing. You look at my mesh, it's still that little bit clumsy, still that little bit awkward. And what I would like to do is refine that. It's because I'm not convinced by using tetrahedrons on that area is going to do it. Now, one thing that can be really difficult when navigating around assemblies is actually grabbing things. So if I go onto my warnings, it talks about, now the good thing is with here I should get stuff that glows. So if I go transparency, so let's go into my warnings. There, that's what I was after. You see there, it refers to the faces that's interfacing around there, and that's what it's not happy with. It's not happy with using tetrahedrons in that case. And if you do come back and you look at it, you do kind of go, yeah, you know what, I can see why. Because it's trying to build that type of face in this condition. You kind of go, what we could do with doing is just building perhaps quadrilaterals in on these faces here, and then letting it go and seeing what happens there. Now, getting to that pin is a pain in the backside. So what I'll do is I'm going to go back to my geometry like this, and you are going to have some fun with this because it's a little bit confusing at first to get used to. So what I'm going to do is just reset. Yes, I'm going to reset that. And up here, you'll see this. It's an eye with a cross through it. You can click to hide. Anything that I click will be hidden. But I can look at hidden parts or unhidden parts. So I'm going to left click. What I'm going to do is I'm going to hide the pin. But you see, it's already hide because it's on domains. I mean, it's on all objects. But if I click onto select domain, I'm going to hide just the pin. You come back and go, that's done nothing. But it has. So if I go to view unhidden, see there that it actually is. But then if I go to view hidden only, now what we've got is we've got access to just that pin. So what I would like to do is go to my mesh. I'm going to drop it and go to user controlled, and that's what it gives me. It gives me the standard, which is fine. I'm going to go to mesh. I'm going to go to more, and what I'm going to do now is just add some free quads. I am going to go on domains. I'm going to come back up to here. I just want boundaries. Sorry. What I just want to be able to do is I just want to be able to select you. Whoops. There. Spin it round again there and there. What I could do is go all the way through. I may do that. But that is the key points that I'm most interested in. Because don't forget, we're talking about components interfacing with each other. They're relating the materials across to each other. So what I'll do is build that. It's coming on from that mesh there. Okay, that's fine. Okay, I'm going to go bolt. There is a surface sitting. Oh my god, I've had a nightmare today with that. There's a surface sitting underneath that. There we go. Earlier, if you remember, I said I was going to turn off my surfaces, and that's what I was doing. That's better. So let me just go back to boundaries. Put them onto here. Remove that. I'm going to go you. And click build all. Mesh face 29. Where's my 29 there? So 29 on here is. I've had a nightmare with this today. Back onto here. It's not liking one of my faces. Swear to God, I've not been lucky with this at all. So let me just bring this to. Hang on a second. Still not sold. Sorry, 1 second. 1 second, just fixing this. Right. Sorry, I was just getting that fixed. It was quite irritating. Right, so what I've actually done with it is I'm onto my mesh in here. Now what I was trying to do is I was trying to navigate around here, and I was trying to show you this. Now you see here what I was actually doing is I was trying to mesh just on these faces and add just quads onto it. Now this was purely because is that going to let me add these in? I was having to just rebuild that. It was just not playing ball. Right, so let me just see if that'll just remesh the whole thing. Right. So what I did is I meshed on the actual caps, if you will, the caps of the pin. Now I could try and add the whole thing in. What I'll do is just stay with that for the moment. And the reason is I need to be sure that the way that assembly is interfacing around it is giving me something that I can genuinely operate with. And if I then hit compute on that, it will take a moment, but what I am able to do is look. Now you'll notice that I've actually just left it on the pin, so we're still just looking at the pin, but we can now plot in between things. So if I want to just look at what the pin's doing and look at how much aggression the pin is actually getting applied to it, I can do that. So you look here, and again there doesn't seem to be much change in between it. We've still got all important deflection. You can see here it moves exactly like I wanted it to. It's starting to get this real centerization around the pin here. A little bit more refinement. I don't think I need an awful lot more refinement, but then if you start to look, you can actually see that it's really concentrated that point. The pin is bending back. It's bending, it's deflecting around that bar. Look at that deflection on the inside of the actual pin. What I can start to do, just to show you if that is transparency, by the way, I'm only just operating around transparency, but what I can start to do is start to see what's happening. Now, see here, this is a little bit irritating. It's something I could fix with the geometry, actually. But you see there, this has happened because it's seen as separate faces. But because that pin itself is interference fit, you can see there that it's really heightened around that pin interface here. Now if we zoom all the way up, we come back up to the actual chuck itself, there is deflection there, but the thing is because I knew that the pin was going to, because of experience, because I knew that the pin was going to be the biggest thing that was really suffering with aggressive responses, that was my key particular point that I was most interested in. So I knew that I'm going to have to refine it. It wasn't any like particular. This does come down to as well of experience of whatever it is that you're using. A lot of people have used this before. They will know. They'll have a good idea of how things will fail, or what it is that you're looking at. Comsol do some great examples of where they've got rotor blades from a helicopter, and they actually just have the blades spinning, but then they put a frequency into it so it starts to bend, if you will, and they try to show. Now, if you look here on my stress plot, what I really want to be able to see is what's happening to the hidden components. If I click plot, oh sorry, that's hidden entities, sorry, that's just giving me the lines. If I click plot, what I actually want to do is propagate hidden to lower dimensions. And what you can see there is I can see just the interface between that pin to the block and the yoke itself. If I want to flip this over, what I will need to do is run it again, but swap around them hidden elements. So if I just click this back in, and I'll get rid of this. So it brings the pin back in. So if I go back to my geometry and I click onto, let's see, all. So I'll view all. And what I really want to do is I just want to hide. So let's have a look at what's presently hidden. View unhidden. So at the moment, nothing is hidden. So what I'm going to do is I'm going to hide. Objects to hide, so I've got demands, I want to hide you, and that's the pin that I'm still interested in seeing. So I'm going to go back. I can't remember if this will allow me to do it just like that. No, it's not actually going to allow me to plot. I'd have to rerun it again to actually drag out the pin, which is a little bit annoying. But what I now know with that is, given that there's very little compressive activity occurring around here, what I could start to do is remove sections out of this rear point of the actual pin. Is that even? It's still solving. I can't believe it. So what I would like to do here is I'm probably going to cut out a section off from here. So if I come back to my geometry, I know we're getting close to time. Apologies. Change it onto my transparency here, and then on here. If I want to do a modification onto this, it is similar to what we did. I'm going to quickly cut a hole to show you what I mean. So if I go to work plane, and then on my work plane here, you can see it's where it's sitting. So it's sitting here. And all I'm going to do on my work plane is for this, I'm just going to model a circle. And let me just get rid of this. Click onto here, and then get rid of that for a second. Click onto here, then I'm going to go sketch, and then I'm going to go circle. Just put a circle like that. And this is just to show you a quick way of being able to do this. So then we'll simply go to extrusion. And I'll just go 500 because I'm only using it as a cutting tool. And then reverse direction. Click on build. That goes all the way through there. I know that's too big, but I'm going to use this as a subtraction tool. I'll go right click. I'm going to go boundary elements. Boolean controller even. So I'm going to build that, and then I will do, and I'm simply doing a difference. So I want to keep that, and I'm going to subtract that, like that. All my conditions are still the same, but what I can do is run that through again. As you can imagine, this is going to be quite catastrophic on the material itself when it runs. And the reason I can run it is the parameters of the boundary were never changed, my mesh has never been changed, and I can run this through again, and I can actually look around in this in particular hole here. When this runs through, what the convergence now does is it will now plot the result, the solid mechanics against the lump. Oh, there we go. Already done. And you look here, and interestingly, because this is structural steel, it deflects that little bit more. You've got that higher grating deflection on that little bit more, but what we've actually been able to do is drop the weight. We've been able to drop that material to it. This would be fine if you weren't conscious of deflection. So if you were saying that we don't care how much, if deflection is increased, it would be fine. But if you are conscious, so if you're in a precision engineering job like that for components, things like that, this would be an instance. This would be a problem. This where you may want to triangulate a little bit more. So obviously with some things you can't just simply say it's all right, let's let it move more. In this case, we've had to really consider how much it moves. Now I know I've rabbited on a little bit, and I hit another bloody problem with this version. I'm going to chase these up today because it's still solving at something like that. I'm going to be looking to try and find out where that came from. I think this is because I'm solving from my desktop, but I will find out today because I've never seen it take so long before in my life. Because this is a copy that I run, and you see it doesn't take long at all. Right, for anybody who's interested, I am going to, that is all I was really going to do today. I really wanted to take you through the parameter changes and introducing that parametric element to it. If we're going to, well, we are going to do a parametric sweep, but what I would like to do is I'm going to minimize the geometry and make it that little bit more consistent so we can have that nice parametric sweep and you can get used to the using of that. What I would then be doing is moving on to shelling. I'd like to look at shelling, the uses of shelling and what it actually does, and how we can control interfaces between composite materials, fuse deposition methods, printing, anything like that. I say printing lightly because printing is a whole monster all by itself. The other thing that I then will be doing is taking you through a time-dependent studies, showing you that, and during that time I'm probably going to give you the assignment out as well. So it's something just worthwhile getting to playing around with at the moment. So get used to using this, get used to navigating yourself around it. I did promise everybody that I would show you, so I should just say, if you do want to run off, you're welcome to run off at this point. Thank you for everybody's attention. But what I did promise you is I would show you something that I personally work on. So I'll quickly show you this, if I can just show it to you. I certainly can. So what I do is I run multiple sets of studies, and some of these studies, one of these studies here took all weekend to run one run. So I'll quickly show you it. It's just to show you as an application where this is found. So 2 seconds, let me just navigate my way through to my work. Under my simulation files, nearly there. So you see here I've got 3.5 gig running on this spinal segment test. Oh, that's a nice one. This one I had to run on the HPC. I will upload this. I will upload the assembly, the working assemblies for you to see it. But what I alluded to is, if it's going to show you. So this is a parametric study, and this is pushing on the back end of a human body. So the body pushes down. We have actuators which are pushing along here. The resistance in here is the interface of hyperelastic material to 3D printed material, and this runs a parametric study of someone lying down through to attempting to sit up, and it looks at 0.1 of a second of the material deformation and changes in it. Now what I wanted to show to you is that there is no difference at all in what we've been doing. The only thing that's different here is my geometries and my meshing procedures are obviously a bit more heavier on here. So if I show you the meshing procedures on here, I've got a combination of quadrilaterals. Let me show you the hidden. Now the hidden one, which is my hyperelastic material, has to be built manually with quadrilaterals and then swept all the way along to create a sweeping action to actually replicate it to make sure it moves like I want it to. So it's a heavy going. It is very, very heavy going. But I just wanted to show you an example of this being used. Right, so I'm just going to stop on my recording.